It's not just a building, it's a $1.5 billion gamble built on the worst imaginable soil. The Burj Khalifa, 828 meters tall with 163 floors, is the world's tallest skyscraper.
But the secret is that Dubai is built on loose desert sand, not compacted earth.
This sand moves with the wind, sinks under weight, and collapses when saturated with water.
Building the world's tallest structure here was deemed impossible by engineers and suicidal by architects.
Yet, the builders accepted the challenge, asking for 6 years to complete the project.
This is the story of a building that defied all structural engineering rules and almost collapsed 3 times.
The core problem in Dubai isn't height, but what lies beneath the surface.
Geological surveys in 2004 revealed 40 meters of fine sand and silt from ancient riverbeds.
This sand has only half the density of solid rock, compacting and sinking under heavy loads.
Initial calculations predicted the towering structure would sink 3 meters in 10 years with shallow foundations.
Uneven sinking would cause the structure to tilt, windows to break, and eventually lead to significant structural compromise.
The solution was brutal. Drill through the sand until solid bedrock is reached.
However, at this site, bedrock was found 50 meters deep, equivalent to a 15-story building.
Concrete piles, each supporting 50,000 tons, were needed to reach this depth.
The Burj Khalifa required 192 such piles, forming the deepest foundation for a high-rise.
Pile drilling began in January 2005, utilizing Kelly rotary drills mounted on crawlers.
These drills, with 1.5-meter diameter bits, descended at 5 meters per hour.
They crushed material and extracted it with helical augers.
However, the loose sand caused borehole walls to collapse immediately after drilling. This problem, akin to digging in beach sand, almost halted the project in its first week.
The solution was bentonite mud drilling, pumping a thick clay water mixture into the hole. This mud, denser than water, kept the borehole walls open via hydrostatic pressure. As the drill descended, the mud pushed against the sand, preventing collapse. The mud filled the hole behind the drill, ensuring stability. Upon reaching bedrock 50 meters deep, continuous mud pumping kept the hole open.
Next, the reinforcement cages were installed, each 1.5 meters in diameter and 50 meters long.
These 30-ton cages were fabricated on-site by welding 40mm steel bars helically.
They were lifted vertically by crawler cranes and slowly lowered into the mud-filled holes.
This delicate operation took 6 hours per cage, as tilting could render them unusable.
Once the cages were in position, tremi-concreting began, preventing contamination. A 30-centimeter steel tube was lowered to the bottom, and concrete was pumped through it.
The concrete, denser than mud, displaced it upwards as it filled the hole.
This process continued until each hole was entirely filled with concrete. Each pile consumed 120 cubic meters of concrete, mixed with retarder additives. These additives slowed setting, allowing concrete to fill all spaces around the cages. The drilling and installation of 192 piles took 9 months to complete. An invisible grid of concrete pillars, anchored 50 meters deep in solid rock, was formed. However, the piles alone were insufficient. A massive raft foundation was needed. This raft distributes the building's weight evenly among all the piles.
The Burj Khalifa's raft is the largest monolithic concrete structure ever poured continuously.
This massive reinforced concrete slab measures 80 by 50 meters and is 3.7 meters thick.
Weighing 45,000 tons, its construction began by excavating the site to 3.7 meters deep.
A 10-centimeter blinding concrete layer leveled the pit floor, where pile heads protruded. Then, 6,000 tons of 25 to 40 millimeter corrugated steel bars were welded into a 3-layer grid.
The bars were spaced every 20 centimeters, forming a dense steel cage.
Concrete pouring commenced on August 1, 2005, with a critical challenge: no stopping.
If concrete cools and sets unevenly, cold joints form, creating structural weaknesses. To prevent this, the entire slab had to be poured continuously, without interruption. This involved 12,300 cubic meters of concrete in 48 hours, a record-breaking pour.
A fleet of 200 mixer trucks operated 24/7, delivering concrete from 30 kilometers away.
Trucks arrived every 4 minutes, discharging concrete into stationary pumps.
Pumps distributed concrete via pipelines, while vibrators eliminated air bubbles.
However, concrete generates heat as it sets, an exothermic reaction.
In a 3.7 meter thick slab, internal temperatures could reach 60 degrees Celsius.
Uneven cooling after setting would cause thermal stresses and crack the concrete. Engineers mixed concrete with crushed ice and embedded cooling pipes to control temperature. Cold water pumped through pipes extracted heat, ensuring controlled curing.
The pour finished after 48 continuous hours, creating a monolithic concrete and steel mass.
It took 30 days for the slab to gain enough strength for vertical construction. During this time, it was covered and watered to prevent rapid drying and surface cracks. With the foundation complete, vertical construction began, facing the challenge of wind. At 800 meters, wind speeds could exceed 160 kilometers per hour during storms. Wind hitting cylindrical buildings creates vortices, generating oscillating lateral forces. If swaying frequency matched the building's natural vibration, resonance would occur. This could exponentially increase swaying amplitude until structural failure, like the Tacoma Narrows Bridge. The Burj Khalifa's geometric solution, a Y-shaped cross-section with 3 wings.
The shape changes with height, with each wing setting back inwards at 26 levels.
This stepped setback confuses wind flow, preventing coherent vortex patterns and resonance.
The design, inspired by the Hymenocallis desert flower, is biomimetics in structural engineering.
Vertical construction began with the reinforced concrete central core, the building's skeleton.
Core wall thickness varies from 1 meter at the base to 30 centimeters at the top.
The base concrete, with 80 megapascals compressive strength, is almost twice as strong as standard concrete. This strength is achieved with high-strength cement, microsilica, and superplasticizers. These additives create an ultra-dense concrete matrix by reducing water needed. The core construction used self-climbing formwork systems, rising hydraulically. Each formwork was 3 meters high. Concrete was poured until it was full. After 72 hours, hydraulic jacks lifted the formwork 3 meters, and the process repeated. The core grew at a relentless pace of 3 meters every 3 days. Teams worked 12-hour shifts, day and night, non-stop. A brutal logistical problem arose: how to transport concrete 600 meters high. Mixer trucks could only reach the base, and crane buckets were too slow. The solution was a giant stationary concrete pump, the Putzmeister BSA 14,000. This machine could pump concrete vertically, up to 600 meters. It was a truck-sized machine with a 60-meter hydraulic mast anchored to the building.
The pump pushed concrete through a 15-centimeter steel pipeline running up the structure.
Pumping concrete 600 meters vertically presented unprecedented problems.
Hydrostatic pressure at the column's bottom was 60 atmospheres, enough to burst pipes. Friction generated heat, risking concrete setting inside the pipe and blocking it. If blocked, the entire pipeline would need dismantling and replacement, taking weeks. Engineers used superplasticizers to reduce friction and allow concrete to flow easily.
They also mixed crushed ice directly into the concrete before pumping.
Tons of ice were added to each batch, melting and absorbing heat. This primitive yet essential technique kept the concrete cool, enabling vertical pumping.
In 2007, concrete was successfully pumped to 601 meters, a new record.
The pump pressure reached 100 atmospheres, causing pipes to vibrate intensely. Yet, the concrete arrived fresh and workable, ready for pouring. As the concrete core rose, the building's wings were constructed with steel structure. Tubular steel columns, 60 centimeters in diameter with 5 centimeters thick walls, were bolted to the core. Steel beams connected the columns, forming the floors. Then 20 centimeters thick concrete slabs were poured. This hybrid system was vertically rigid yet laterally flexible, allowing for sway.
The building could sway up to 1 meter at the tip during extreme winds without damage.
However, a bare concrete and steel building is not habitable. It needed a skin.
The Burj Khalifa's cladding consisted of 24,348 glass and aluminum panels. In each 3 by 1.5 meter prefabricated unit, combined reflective glass with anodized aluminum frames.
The low emissivity glass, with a microscopic silver layer, blocked heat but allowed light. This reduced solar heat gain by 40%, crucial in Dubai's desert climate. Panels were manufactured in China, shipped to Dubai, and stored in climate-controlled warehouses.
Installers worked from suspended gondolas, lifting and positioning panels with laser precision.
Panels were fixed with stainless steel bolts and joints sealed with structural silicone. At peak, 175 panels were installed daily, and the complete cladding took 2 years.
By 2008, the building exceeded 600 meters, becoming the world's tallest structure.
However, Concrete could only be used up to a certain point due to its weight.
Beyond 700 meters, the core walls would be too thick, consuming usable interior space.
The solution is to switch to a steel structure for the upper spire.
The 200-meter, 4,000-ton steel spire was fabricated in sections in India.
The ingenious problem: no crane could lift the spire 800 meters from outside.
The solution: assemble the spire horizontally inside the building. Then, push it upwards telescopically from within, using hydraulic jacks. Spire sections were stacked horizontally on upper floors, then pushed up. The first section was pushed through a roof opening and welded into position.
The second section was pushed upwards inside the first, like an extending telescope. This process repeated 20 times until the entire spire was extended, taking 3 months. On January 9, 2009, the last spire section was placed, reaching 828 meters. The building was structurally complete, but a new problem emerged: removing the cranes. The cranes were at 800 meters, too high for external cranes to dismantle. The solution was a cascade dismantling sequence, taking 4 months. The largest crane dismantled the second largest, and so on, down to the smallest.
The smallest crane was dismantled into pieces light enough for the elevators.
The building officially opened on January 4, 2010, costing $1.5 billion.
It houses luxury residences, corporate offices, the Armani Hotel, and observation decks.
The AC system consumes 40 megawatts, powering a city of 10,000 people.
Elevators travel at 10 meters per second, the fastest in the world in 2010.
However, the building has a dark secret. It's not connected to Dubai's sewage system. Wastewater is stored in basement tanks, then trucked to treatment plants daily. This temporary solution became permanent, highlighting ambition over practicality. Built on the worst soil, in a hostile climate, during a global financial crisis, it stands. Engineering sometimes proves the impossible can be done, even if only once.
Subscribe if you enjoyed the video and want to see more like this.